Before moving to cryptography, encryption, and cloud security concepts, let us briefly cover the physical security aspects. All network equipment and software applications require actual physical data centers to get compute resources. Securing these data centers, authorizing access to them, ensuring server layout, cabling hygiene, and maintaining the data center environment are equally vital for secure, highly available services. Hello, welcome to the next episode of Get Certified Together program by TechnoCoff, your free online knowledge sharing community. Visit our website, www.technocoff.com for more information. In this episode, we will be covering the next section of the CompTIA Security Plus certification exam. For Section 2 of the CompTIA Security Plus exam, Architecture and Design, we will be covering various topics ranging from enterprise security architecture, virtualization, cloud, code security, cryptography, physical security, and cybersecurity resilience. Let me start with the very first topic. Secure code design. Softwares are part of our life now. We use advanced devices like smartphones, smart television, GPS-enabled cars, and so on. All these devices need some sort of software application to run on the physical device. Every software application is written in the codes, and deployed in two ways. In client-server model, the application is deployed centrally on a remote server and used by clients via the internet or intranet. Another deployment type is client-side model, where an application is installed on the client device in form of a local application. Every software needs to be written with a standard coding language, tested, and delivered to clients. This cycle is termed as software development cycle. The software development cycle begins with the RFC, or request for change from the customer. After this, the code is written, or updated, and post proper change management approvals, it is deployed to production. It may not be desirable to deploy newly written code directly to the live production environment. Hence, we need three different environments. The development environment is the one where the software development takes place. The testing environment is used by the quality assurance team to perform testing on new codes. Once testing is completed, the code is pushed to the staging environment, which is identical to the production. Pushing the code to the staging environment helps to check compatibility with the actual production setup. Lastly, code is deployed in the production environment, where it is used by the clients. This whole process used to follow the waterfall approach, where every change requires a new software development cycle. However, to reduce time and avoid wastage of resources, organizations follow agile methodology with short sprints of deliveries. This helps in enabling C/CD or continuous integration, continuous deployment. Just now I talked about the software quality assurance team. This team is responsible for ensuring code is tested and reviewed properly before deployment. How does it work? Well, the first step in the software quality assurance is the code review by any senior team member or team of reviewers in the organization. Software should then be validated and verified with the initially agreed business plan to ensure all requirements are met. Post-verification, the code is tested using static and dynamic tests to determine code behavior in different situations based on the input provided. In static code testing, the software is validated according to standard coding practices and recommendations. In dynamic code testing, software behavior is verified by sending actual input data under different load scenarios to identify potential issues users may face. Fuzz testing is an automated way of testing the code behavior by sending malformed, invalid, or unexpected inputs to the software. CompTIA exam covers questions from this section because an improperly tested code may lead to vulnerabilities, which can later be exploited by the attackers, resulting in risk to end users. All codes written must be stored centrally with proper versioning standards to ensure both developers and reviewers have visibility on the latest version of code and all changes committed in the new release cycle. Code repositories like GitHub or GitLab are mostly used by organizations. They are vital for source control, code integrity management, and avoidance of the dead code in any application. Dead code is a scenario where the developer adds new lines to application code, but forgets to remove unused or old lines. This may lead to unsuspected vulnerabilities in the software. While I talked about all these vulnerabilities, which may be caused by mistakes in writing the code, or improper error handling during testing, we also need to know to fix them, right? Well, the fix for most application code-based vulnerabilities is patching or software updates. Organizations can use an umbrella system to update and apply the latest patches on remote devices connected via the organization's intranet. This is also a good time to talk about zero-day vulnerabilities. Any newly released software may have a vulnerability which is yet to be identified. Patch for these vulnerabilities is only developed and released by software owners once this zero-day vulnerability is identified in the application and reported in the CVE database. Now, I have talked about secure code design practices. However, when an application is installed, using a tested and verified code, attackers will not be aware of the hidden vulnerabilities right away. They have to attack the application first, to identify and exploit vulnerabilities. They are application-level attacks. Open Web Application Security Project, or OWASP, provides a comprehensive analysis of different situations in which an application may be attacked and made to work in an unexpected way. Few commonly faced scenarios are incorrect data input, wrong or insecure application design, unhardened baseline software, unpatched or vulnerable components used in the application, or improper monitoring procedure. Let us discuss about various key types of application attacks, commonly asked in the exam. First is SQL injection. Most web applications use some kind of database in the backend for storing user data. In an SQL injection attack, the attacker uses malicious SQL code to manipulate applications and access the information stored in the database. For example, they may use the select star statement of the SQL database to query the whole table. The input validation technique is important to prevent these kinds of attacks. Another form of web-based attack is cross-site scripting, where the attacker places a malicious script on an authentic website, waiting to be run by the visitors. Another similar form of attack is called the cross-site request forgery, where the malicious script actually sends requests, on behalf of the user, to another website open in the same browser window on the client's device. One more web-based attack exploiting user input is the buffer overflow attack, wherein the attacker sends incorrect bulk of input values, expecting unexpected behavior from the underlying application code. Attackers may also look to exploit cookies, which are stored on a browser and shared across, in the HTTP request by a user. Cookie guessing attack revolves around this similar strategy, where cookie values for any authentication session can be guessed, using session hijacking, and reused to access a web account. In this case, the attacker passes the hash value as a password, once it is extracted from the cookie message. We may have a scenario where attackers may try to execute malicious code directly on the server side, or tries to gain privileged user access to the application. These two scenarios require high competency, and are extremely tough to execute. But on another side, they have larger implications than simply hijacking user sessions. If successful, they can bring down the whole application for any user to access. To overcome this, applications should follow the practice of least privilege access, and regular patching of underlying software components. Another important thing to understand, while enhancing application security, is the concept of system drivers and memory. Every application runs on the compute resources with hardware drivers and system memory to run processes. The performance of an application can be degraded by issues like memory leaks, null pointers, and DLL injection. For example, in memory leaks, the underlying system assigns memory to the process but doesn't release it when the process stops. When I was talking about different sorts of application-level attacks, I also gave an idea of how to overcome them. Let us discuss them in more detail now, as you will find a lot of questions from this particular topic in the exam. The first strategy for securing applications is input validation, or simply keeping a check on input provided to an application. It may be based on certain criteria, like in the date of birth option, the user should not be able to input a string of alphabets. Input validation can be implemented on both server side and client side, although the recommended approach is towards the client side. It works by creating the whitelist or blacklist conditional rules for the different options in the input. Additionally, for ensuring that only authenticated users can access an application, we need to make sure that all passwords are hashed and salted to avoid sending user information in plain text. For session messages between client and server, all messages must be encrypted using TLS-based HTTPS sessions. Another security strategy for the application-level attack is output encoding. Output encoding is a method to defy users from sending parameters or tags, like in the SQL injection attack. Web applications in this case will encode any special parameters, like the select *SQL statement, and replace it with a random code, so that the backend database doesn't receive a SQL query as the input. To trigger an unexpected event, we use the concept of error handling. Error handling provides the application with specific steps, or error messages, to report whenever received unexpected input, for example in a buffer overflow attack. By now, we get an idea about how important it is to keep your code secure. Another thing to keep in mind is that developers don't write whole code for an application from scratch. To save time, they may use third-party binaries and libraries. This may provide another probable attack surface to the application. Code signing ensures that all third-party codes written as part of an application are digitally signed by a reliable software owner or developer. At the database level, database security covers encryption for the data at rest. Database activity should be monitored regularly for identifying any irregular changes or updates in it. Data entries for any application's database may include PII, or personally identifiable information, like date of birth, name, social security number, etc. Such information must be stored in hidden or obfuscated values using masking, hashing, or salting techniques. This ensures that anyone, even if able to access the database, still cannot read the information in the plain text format. This is called data obfuscation. Various methods associated with this are data masking, where some values of actual data are hidden by false data like XXX, to ensure privacy. Data tokenization, where actual data is replaced with meaningless values. Before moving to cryptography, encryption, and cloud security concepts, let us briefly cover the physical security aspects. All network equipment and software applications require actual physical data centers to get compute resources. Securing these data centers, authorizing access to them, ensuring server layout, cabling hygiene, and maintaining the data center environment are equally vital for secure, highly available services. The first concept to understand for physical security is environmental protection. This is because data centers are highly susceptible to actual physical damages caused by the internal and external environment. Various factors, which can be covered in this protection, are temperature, which is managed by cooling and hot and cold aisle approach, fire, which is controlled by various types of fire extinguishers and water sprinklers, and natural disasters, which are handled by creating hot, cold or warm standby site. In the hot standby site, servers are always up and ready to take over the active site, in event of an outage. In a warm, standby site, the server may have the latest application, but are in a shutdown state, hence taking time to take over the active site. In the cold standby site, only infra is present, and applications first need to be configured before they can take over the active site. Besides planning active, standby site mode, ideal disaster recovery planning involves setting up sites on different geolocations, along with a mechanism of restoring faulty systems, with their recent backup. RTO, or Recovery Time Objective, determines the time taken to recover a system, without impact on the business, while RPO, or recovery point objective, determines the state of the system to which it's restored. Backups may be full, incremental, or differential. Incremental backup involves backing up the change since the last backup. Differential backup involves backing up change since the last full backup. Another key aspect of physical security is access control. This is because access to the data center should only be provided to authorized persons, using various methods like biometric or physical locks, secure man-trap doors and motion, video, or noise sensors. Data storage sanitization is another important concept, which basically revolves around how data is stored in your data center. Data stored on disks or paper must be removed in a way that cannot be recovered after the destruction process. Cleaning, purging, and destroying are 3 ways to remove digital data, while paper shredding is recommended approach for written data. Commonly used methods for purging are degaussing and cryptographic erase. In the case of data cleaning, data is overwritten and filled with zeros. The last topic of this week's podcast is business continuity planning. The business continuity plan is important for identifying the business critical systems and the risk associated with them based on business impact analysis. For BCP, system owners can design their application in fault-tolerant, or HA mode with help of load balancers, to ensure minimal impact on the mission-critical applications. Various single point of failures in physical infrastructure is the power supply, storage, and networking. For the power supply, the recommendation is to use dual source. For storage, the recommendation is to use RAID. Example: RAID 0 provides data striped to 2 disks, while RAID 1 provides data mirrored across 2 disks. For networking, the recommendation is to use multiple paths and port teaming. This brings us to the end of episode 3 of the Get Certified Together podcast from Technicoff on the CompTIA Security Plus exam. In episode 4, I will proceed to pending topics of section 2, like cloud security, encryption, and cryptography. Thanks for listening.
What does innovation sound like? It sounds like the luxury of being in the moment with your customer, client, or patient. It sounds like having the right information right when you need it. It sounds like being at your best for your customers and your business. Thanks to Hyland's intelligent content solutions that improve digital processes, innovators everywhere are able to do their thing better, whatever that thing is. Now, who doesn't like the sound of that? Hyland, for innovators everywhere. Visit hyland.com.